In our previous video, we wrapped up with saying that the way an image is actually processed is via this process called a convolution, which is taking a special type of matrix called a kernel and combining it in some strategic way with our image matrix. Okay, so the kernel is just a small square matrix. Okay, that's valuable to know here. It's going to be a square matrix, so n by n, that mathematically manipulates pixel values through taking a linear combination of the actual pixel values themselves. A linear combination means adding and scaling. The values in this matrix determine how the pixel values will be affected. So if you change the values in the kernel, it's going to do something different to your image matrix. That matrix is called the kernel, and the procedure of using it on the image matrix is called a convolution. Now, the kernel can be a variety of different sizes, but typically at a pretty basic level, it's going to be a 3 by 3. So it's a square matrix, 3 by 3. And by applying the kernel to a 3 by 3 region of the image, okay, so we're only going to focus on, if we're working with a 3 by 3 kernel, then we're only going to focus on a 3 by 3 portion of our image. Now we can adjust the value of, so what do? Well, we don't adjust 9 values at the same time. We don't, we were taking a 3 by 3 and manipulating a 3 by 3 within our image. We're not going to change all 9 values of them, but we are going to consider all 9 of those values in order to change the central value. Okay, so it's the central pixel that we are going to be changing, and we're just going to weigh the pixel values surrounding it. So let's kind of give somewhat of an intuitive basis for this. So let's say that this is our input image. Okay, we're going to call this input image, we call this matrix Y. Kernel matrix, we're just going to go ahead and call that capital K. And so let's say that what we're focused on right now is we want to apply a change to the central pixel here in this 3 by 3 region. Now we're going to do this for pretty much every pixel in the image. Okay, so right now we're just focused on this pixel, which is in the, notice 1 to 3rd row, 1 to 3rd column. And in order to change that, we're going to take our kernel and we are actually going to combine these values. We're going to multiply in a strategic way the values in the kernel with some corresponding value in this little 3 by 3 submatrix within our image. Okay, so we're going to take this 3 by 3 and we're going to focus on that and our kernel, and we're going to produce some multiplication process of these values, and we are going to generate a new little matrix. Okay, so in this case, in this particular example, this is not exactly how we're going to conduct it, but notice that what's happening here is -1 times 7 gives you -7, 0 times 3 gives you 0, 1 times 4 gives you 4, and so on. And then, of course, we get 9 values because we've done 9 multiplications. But then the process of, well, what do you do with these 9 values in order to generate a new number for that central pixel, which is the one we were set out to change in the first place? We're not going to change the 7321734. We're not going to change those. We are only going to use those to help us change the central value. So what we're going to do is we're going to sum them up. We're going to add them together. So this is an element-wise multiplication, not the way we typically do matrix multiplication. It's a little bit different. It's actually doing kind of what we maybe originally thought matrix multiplication looked like, just taking element-wise multiplication instead of the weird dropping columns and multiplying out that way. So then when you sum these values together, -7 plus 0 plus 4 plus 6 plus 0, or plus -6 plus 0 plus 6 plus -2 plus 0 plus 7, 2, and now your value of 5 has become a value of 2, and now you move on to the next pixel. And this is kind of how this process goes. The only thing to note is that you are, when you change that value, you're not changing it in the original y equals. We would call this something different, like maybe y new, right? Because if we then take this matrix, which now has the 5 changed into a 2, and we apply the kernel to, say, the next pixel over here, well, then it's going to be using this 2 And that's going to kind of mess things up because we can't be manipulating values based on manipulated values. So we're always going to be basing things on the original input image, and this new output image will be a copy of sorry, not a copy, but it'll be a brand new blank version of the input image. So it's a function that we're applying to it. And the question is, well, how does this kernel get applied exactly? So we have to deal with kind of a funky sum here. This is not our standard matrix multiplication. This is called a discrete convolution. Now in calculus, there is actually an integral version of a convolution, and it has many applications. So let's define y to be the image pixel matrix of size m by n. Okay, so that's our actual picture, right? As we said, it has 1 to m rows, 1 to all the way up to n columns. And then we're going to have this p by p kernel matrix. Now we're going to focus on 3 by 3 here. Okay, so we're going to have this little 3 by 3 matrix, and we are going to then consider one pixel value at a time. Now the first thing we have to deal with is this convolution formula. So it looks kind of weird, kind of strange, but what you should notice here is that the way this is read, this thing on the left, is this is the convolution of y and k. Convolution of y and k at location row I, column j. Okay, so you have many convolutions that take place. Every pixel is one single convolution. And it's this, notice that it's going to be this times elements of k. Now, I do admit it is a little bit strange, but let's say that what we want to do is we want to do a convolution. Okay, we kind of use this star, y star k. And let's say we want to apply this to the position maybe 4, 5. So the way this sum works is, notice that this goes from -1 to 1. In order for this to mathematically make sense, we kind of have to relabel our row and column values. Instead of starting at 1, we typically start at 0. Okay, and that's the way a lot of coding languages work, is that let's label, for mathematical purposes, let's label our matrix to go 0, 1, all the way up to m minus 1. So basically we're just knocking off 1 from every single row value. And then here we're going to label our columns 0, 1, all the way up to n minus 1. It just makes the math a little bit easier to work with. And we'll do the same thing with our convolution, our kernel matrix, except that we are going to label these -1, 0, and +1. And again here, -1, 0, and +1. Okay, the reason this is going to make sense is because every time we move into a different pixel value, we're always referencing the same location in the kernel matrix. So the way we start a double sum is we first of all set the outer sum to its minimum value. So b is going to go from -1 to 1. Notice that there's a b here and there's a b here. And then a is going to go from -1 to 1. Okay, so that's going to be this value and this value right here. Okay, so let's just write this out for a 3 by 3 kernel matrix. So if we were focused on the location 4, 5, okay, let's see, that would be somewhere over here, right? So there would be kind of our little 3 by 3. There would be the central pixel value 4, 5. Now, this formula says, okay, first of all, set your b value to -1 and set your a value to -1. So what that means is, okay, well, remember our I and j in this case are 4 and 5. Okay, 4 and 5. Actually, let me write it down here. B equals -1, A equals -1. And I want us to be able to read this notation, be able to make sense of it. And the way it often makes sense is just to write it out and see what this is actually saying. Okay, if B is -1 and A is -1, that means we're going to take the Y value at, let's see, 4 minus -1. Okay, 4 minus -1 is 5. And then 5, J is 5, so 5 minus -1 is going to be 6. So in terms of this little box right here, let me blow this up a little bit. Let's pretend that this is in the image. Split this up into a 3 by 3. This is the location 4, 5. Okay, so if we do 5, 6, well, that's going to mean that that's the next row down, right? Because this is row 4, this would be row 3, this would be row 5. Here's column 5, this would be column 4, this would be column 6. Okay, so we're in row 4, column 5. We're going to take the Y value at the location 5, 6. So that's going to be this guy right here. Okay, here is 5, 6. And what are we going to multiply that by? We're going to multiply that by the kernel value. That's going to be this guy here. This is our K matrix. We're going to multiply that by the K value at, okay, B is -1 and A is -1. So that's going to be the kernel at position -1, -1. So that's going to be this guy right here. -1, -1. Great. Okay. So notice how we're actually not multiplying the way you might think. We're not taking this value, this top left times this top left. We're actually taking the top left times the bottom right. So now the way a double sum works is you leave the outer sum, or the outer index, -1, at -1, and you increase the inner index. You always increase the inner index until it maxes out, and then you go back and increase the outer index. So now B is still -1. A will go from -1 up to 0, because we're going to go -1, 0, and then 1. A equals 0. Okay, let's again recalculate this. So this will be Y at position 4 minus -1. That's still going to be 5. 5 minus 0 is 5. So notice that we've gone from the 6th column to now the 5th column. So what entry is that going to be? That's going to be this guy right here, 5, 5. So we've moved over to the left a column. And in terms of our kernel, that's going to be at K of B, A, so -1, 0. So in our kernel matrix, we are now at this position right here. Let me adjust this a little bit. That's better. -1, 0. So notice that in terms of what we're multiplying, in the 3 by 3 of our image, the 3 by 3 matrix subset of our image, we are moving from bottom right to top left, and then we are moving from right to left, ascending up the column, up the rows. In our kernel matrix, the value that we're picking is top left, from left to right, and we are moving down the rows. So notice that we are going to go, first of all, we're going to go this way, and then we're going to move our way up and to the next row and the next row, and except here we are moving from the top left to the right, and then we're going to move down across each row. Now this is going to be true for the next one. Let's just do one more value to see that this is also true. Again, now, because we're done with A equals 0, A can still change. A goes from -1 to 1, and so now A will become +1. This means that Y at 4 minus -1, so we're still in the 5th row, J, which is 5, 5 minus 1 is 4. So once again, we are now in row 5, 4. So we've decreased our column, maintained our same row, multiply that by the kernel at b comma a, which is -1 comma 1. Okay, -1 comma 1 is right here. And you can see again, we're moving from left to right. Now, these are all going to get added together. These are all going to be added together. That's the important part here. Once we're done, because it's the sum of all of these. And just to show you now, okay, now that a is at -1, I'm sorry, a is at +1, and a goes from -1 to 1, we've maxed out all of our values of a. We've done all of our indices of a. So at this point, now you move back to the outer sum and you say, okay, well now I need to increase that. B starts at -1. B will now increase to 0. And now you reset a. It's like resetting the clock. So start back at a equals -1. And you do b equals 0, a equals 0. B equals 0, a equals 1. So now, and you can verify this, this will be 4 minus 0, which is 4, and 5 minus -1, which is 6. So notice that we're now right here, 4 comma 6, in terms of our kernel, will be at b comma a, 0 comma -1, 0 comma -1. So once again, we've just changed the row. That's what the outer sum does. It changes the row. The inner one operates on the column. And then, of course, now we're going to do b equals 0, a equals 1. And then after that, we would do b equals 0, a equals... I'm sorry. Back here, this should not be... It should be a equals 0. And then here, this will be a equals 1. Okay, then we would go, since we've maxed out a again, we would now jump to b equals 1. Okay, so now we would be in the third row of the kernel, but we would be in the first row of our subset matrix. So that's how that summation works. It is really strange. There is a good reason for it. Yes, it can be done the other way around. Yes, it seems overly complicated and weird, but because mathematically convolution has other applications, it just makes sense to stick with the original definition of a convolution because it has certain nice properties as well. So in the next video, we'll actually take a look at one sample computation and see how this all pans out.